Okie doke, we're rolling. Woo. Alrighty, friends. So, yep, everybody seems to be doing web work. That's good. There will come more time for that. But first, story time. And actually, even more primal than that. Does anyone need an upper division math course sheet for the spring? You can get these at any time. They're around. I kind of got them all. So this Calc 2 is actually a prereq for a number of courses. You guys see visual in these upper level math class listings? Yeah. And if you change your mind, I got them here. If you want 2, you can have 2. I've got more than I'll need. I got 4 people in abstract algebra. So pretty good. Okay, so story time. Story time. Got a great story to tell you. Did you need one of those, or you already got one?
No, I got one.
You got one. Okay. Oh, right. Okay, so if you would just join me, that's all I ask. Just join me for this, hopefully not too long story. So we have been. First off, the big thing I want to talk about a paradox in math, and we're right at the spot where this paradox could be understood and arrived at. So Gabriel's horn paradox. This is a classic paradox in math, and in particular in Calc 2. And there's going to be a bunch of weird things that this class is kind of the gateway to see. This is really the first one. There's more to come. And I know that the sum stuff is not in your wheelhouse, but there'll be more of that, but this isn't that. But it might be equally disturbing, so I don't know. We'll find out. First thing I want to talk about is, we have to build up to this really quickly. So let's just talk about length of a curve. And honestly, you don't need to write any of this down. I would actually prefer you just enjoy and try to follow, because I won't ask you to do any of this. Just like you went to a math talk, maybe the first math talk you voluntarily went to. So length of a curve. So I've got this function y equals f of x on some closed interval. I'm going to kind of whip through this in a way that I normally wouldn't. So I got my function. I want to know how long that thing is. So if that were a piece of string and I could straighten it out and measure it, how long is it? Now some curves that's easy for, right? So if I gave you this and told you that was a straight line, we could figure that out. In fact, we would just need to know the change in the y over the change in the x, and then we would summon Pythagoras. I used to go through a big show with that, but I'm not going to do it now. Pythagorean theorem tells me that the length of that thing is the square root of the sums of the squares of the sides. Does this sound reasonable? A squared plus b squared is c squared. Yeah. So thanks to Pythagoras, we could do that. But the minute this thing becomes anything else, especially some crazy, unpredictable function, yikes. Don't know what to do. But we have calculus, and we know what to do. What we're going to do instead is cut this up into little pieces, use this, pretend each piece is straight, add up all the lengths, and go ahead with our business. Now, I mean, so if you just had a ruler on you and I said, how long is this? You could estimate with the ruler, right? You could take it and go, well, that little bit's that little bit's that, approximately. And that's how you would estimate roughly how long it is. And that's what we're going to do with calculus. So the first thing I'm going to do is cut this up into n equal pieces. x1, x0, x1. You've seen this story a bunch of times. And then I'm going to, on my curve, grab the points that are above my cuts. And add them all up. Let's see what that might look like. So the approximate length would be the sum of each little piece. And each little piece is going to look like this. So let's see, here's my curve. this is delta x, this is delta y. And delta y is actually, if this is x sub I and this is x sub I plus 1, then this height here is f of x sub I and this height is f of x sub I plus 1. So just getting everything all lined up, I just want that length right there. And this delta x might change over time as well. So let's write out what this is going to be. It's going to be the sum of all these little pieces like this. And that's going to be the square root of delta x squared plus delta y squared. So this is where I took the ruler and I'm just straight edging everything and adding them all up. So that looks pretty weird and rough. I'm gonna tweak it just a little bit. I'm gonna factor out a delta x from this. So this is some square root. I'm gonna write this and then maybe you can tell me if this looks okay. This might be a manipulation that looks a little intense for you if you haven't seen it. Basically what I did was I took this thing inside here and I factored out delta x squared, and I'm left with 1 plus delta y squared over delta x squared. So just imagine pulling this delta. If you go backwards, this times this is that, this times this is that. And then I pulled out the square root of delta x and that became this. That's the basic idea. I almost don't want to look and see if anybody's super confused because it's like it's not the heart of it, but try to follow along. It won't matter in the end because we're just going to get the formula out. So now this thing here is a little bit tricky. And what I'm going to use is this thing called the mean value theorem from calculus. And I know in my class we didn't hit on it really hard, but basically it says that if you take the average slope on a curve that's differentiable, at some point inside the curve, x sub I star, the tangent slope matches that average slope. So that's the trick of the mean value theorem, that your average slope between 2 points is attained somewhere as a tangent slope. And that's what's essential here because this is just the average slope between these 2 points. So what I'm going to use is the mean value theorem, which says that this quantity here is actually the derivative at some point between here and here. So it's an f prime of x sub I star, and then I've still got my delta x out here. That's it. Now I'm going to let n go to infinity, and this becomes integral a to b square root 1 plus f prime of x quantity squared dx. And that's how you find the length of a curve, with that formula right there. If you know the formula, y equals f of x, then all you have to do is find its derivative, square it, and crank this through. Turns out that all the problems you would ever encounter in a calculus book to use this are just bogus and like forced. It's a really hard formula to do by hand. So they make up cheesy examples to make it doable. We're not going to do that. But that's how I find the length of a curve. Okay, but that's not really what I wanted to talk about yet. That's part of the way there. What I want to talk about is if I take this curve here and I spin it around the x-axis, what is its surface area? So now I'm taking length and turning it into a surface area problem. So this thing here, we spin it around. You've seen me do this little show before, like so, and blah, 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 blah. So I want the surface area of that thing. So what do you think we do? Well, we cut it up into a bunch of little pieces. Imagine what that would look like. I'm going to cut this axis up, and I'm going to approximate. It's a little bit different than what we normally do. I'm going to approximate each little piece on the surface of revolution with a frustrum. So a frustrum is a shape where you have an open circle and a bigger open circle, or maybe a smaller one, and you just connect the two edges. So this is hollow right here. It's a hollow, it's a frustrum. It's actually just a piece of a cone that if you just cut off the tip of the cone, that's what you get. So imagine an ice cream cone, cut off the bottom of the ice cream cone, you got a frustrum. It looks like a little stand that you could make. I don't have any frustrums in here, but imagine a little pedestal that like a poor elephant tortured in some circus would have to stand on or something like that. Except this frustrum, the poor elephant would step in and would be hollow. So it's just the outer edge of it. So, frustrum. What about frustrums? Well, if I have a frustrum that has an inner radius R1 and a second radius R2, so those could be different, and then an outer length L, the surface area of that frustrum is the average of the radii times 2 pi times this length here. So notice that actually simplifies to sum of the r's times pi times L. So I'm going to use that formula. And what I'm going to do is cut this thing up into a bunch of frustrums. And what it would look like is this. It would have frustrum 1, frustrum 2, frustrum 3, and so forth. So it starts to look like stacked frustrums. But each one of these I can actually find the area of, the surface area, using that formula. So let's get to it. It's going to look like this. I need a different pen already because I feel like this one's choking out. Don't worry, we're almost done with this part. This isn't the paradox either. This is just like getting to the paradox. We're traveling to the trailhead. We're taking a bus together, Kitra, to get to the trailhead. Yeah. So I want to add up all those areas. So the surface area is going to be approximately the sum of the surface area of each frustrum. And what that's going to look like is sum, whatever, I goes from 1 to n. Using this formula now, the inner radius is going to be f at the left end point. This is going to be f at the right end point of my cut. And then I've got a pi up front here. I can pull that out. And then the length of that piece, which is going to be this thing again. So square root of 1 plus delta y over delta x quantity squared. So just kind of following with what we had and using the formula. So now I'm going to do some magic here on this thing like I did before and replace it with the value of the derivative of f at some key point in between. So here's what we got. Here's a quick picture. Here's xi, here's xi plus 1, and then somewhere inside there is xi star. And then my delta x is out here. So now, when those points get really close together, when these 3 points are so close together they're almost indistinguishable because we've got infinitely many of them or close to it, the value of f at all these points is about the same. So what I'm saying is that when xi is approximately xi star is approximately x of I plus 1, then this value and this value are the same, roughly. And they're actually the same as this middle one. So I'm going to replace this with, oh shit, I lost my 1/2. Where did my damn 1/2 go from?
Did you cut it off because it canceled out with 2?
Yeah, I did. I'm gonna cheese out right here and just say, I'm gonna put my 1/2 back in for a minute because I need it. And I lost it somewhere, but it's okay. I think I screwed up on somewhere on that formula over there. Yeah, probably. That's okay. So this is f of x of I star plus f of x of I star, because it's the same roughly as the 2 endpoints. And then this is 2 of these, and half of those gets me 1 of them. So my formula, and I never do this constant rewriting, because this would be a mess if you were trying to actually deeply understand it, is just f of x of I star times that. Take my limit as n goes to infinity, and my formula turns into pi integral from a to b, my function times the square root of 1 plus the derivative of my function squared dx. This is the surface area. Whew, I'm glad to get through that. I mostly just wanted to get through that so I could just get you the damn formula. I could have just given you the damn formula and you'd been like, oh, that's nice. I'm glad he didn't explain it to us. Too bad. Sorry. So here's my surface area formula. So now let's get to the paradox. Gabriel's horn. Who's Gabriel? Who do you think? Somebody tell us. Who's Gabriel?
The angel.
The angel, yeah. What is Gabriel's job?
Blow a horn.
To blow a horn, exactly. You've heard of Gabriel's horn, right? I think Gabriel's like when if Gabriel showed up, things were probably going to go bad for you. I think it was like kind of like coming to call on you for something, you know. So that's where the name of this problem comes from. And Gabriel had one hell of a long horn. In fact, Gabriel's horn was modeled off y equals 1 over x. Of course it was, which is asymptotic and keeps going out that way. So we're going to start that at 1, and we're going to spin that around the x-axis. So Gabriel's horn is an infinitely long horn. It looks like this. It just gets narrower and narrower and narrower. Checking on Cassie. Yeah. All right, cool. How do I find the volume of Gabriel's horn? You should know this. You just don't know about the infinite. We haven't done an infinite one, but what is the volume of Gabriel's horn? What formula do I need to use?
2 pi.
Other one.
The 1 pi.
The 1 pi one, yeah. So volume is pi integral from A to B, 1 to infinity. Yeah. Then what do I do with the function?
Outer minus squared.
Squared. Yep, just squared. So like that. So that's the volume of Gabriel's horn. Now we could, and you could, do this problem. You would just do it like you would do any improper integral. What you'd find out is that this is actually equal to 1. It converges. Because think of it, it's 1 over x squared. Remember, we had that little rule with the p at the bottom, and when p was bigger than 1, it converged. And here, p is 2, and you can actually work this one out. The volume is pi. So the volume of Gabriel's horn is pi units cubed, whatever our units are. Here's the paradox. So we could think of this as a paint can, right? Like a really weird-ass paint can. Gabriel's like getting a second gig, not paying enough doing the Gabriel thing, gets a gig, selling paint or being a painter or something. And so Gabriel takes the horn and is like, well, I've got this horn, I guess I could use this to hold the paint. So Gabriel fills it full of paint, and it holds exactly pi units cubed of paint, maybe inches cubed, whatever, cubic feet, whatever you want. Filled up with paint. Filled with paint. Let's figure out the surface area of Gabriel's horn. So the surface area, we'll just use our formula, which is right here. Thank goodness. Let's see, so we need the derivative. So let's do the surface area. I need f prime of x. So that's the derivative of 1 over x. And negative 1 over x squared, sound reasonable? Right? You could write that as x to the negative first, right? Don't forget how to differentiate, right? You bring that, So that's going to go in here, and then I just got good old f of x. So the surface area is going to equal pi integral from 1 to infinity, 1 over x, which is my curve, square root of 1 plus negative 1 over x squared dx. That looks horrible. And it is. We can't do that integral. But we can understand something about that integral. Let's rewrite it one more time. We're almost done with the paradox, and then we can start working on freaking web work together. But this is 1 over 1 plus x to the 4th dx. How does this, what could we say about this? What is that always greater than? Greater than 0 for sure. Is there a higher number? Agreed. 1. It's always greater than 1 because this is a positive number, right? So it's always a little bit bigger than the square root of 1. So this is bigger, it certainly is bigger than 0, but even more precisely, it's bigger than 1. So this integral must be bounded below, so let's compare. It's got to be bigger than this integral. I'll just replace this with 1. Right? If this piece is bigger than 1, then it must be bigger than this integral. Does that make sense? The integrand is bigger. So you get more. What does this integral equal? Remember the little p rule? Somebody just dropped something off at my house. Let me help you out. This is going to be, and I'm going to cheese this out. This is going to be natural log of infinity minus natural log of 1. So that's terrible, but it's the idea. What's the natural log of infinity? Infinity. Natural log of 1, 0. So this is infinite. So Gabriel's horn has infinite surface area. It doesn't hold enough paint to paint itself. But the paint is touching everything on the sides. But there isn't enough paint in there to paint the damn horn, even though the inside would seem to be clearly painted by being filled with paint. So that is the paradox, that we have this object that has finite volume but infinite surface area, and the good way to think about this is it can't hold enough paint to paint its own self. Does that seem strange? Yeah, the faster you tell me yes, the faster we'll be done. So yeah, that is Cassie knows how it is. Yeah. What does it doesn't seem strange?
No.
Dude, damn it, Lou. So anyway, I won't go through, we could spend hours talking about what is going wrong here. Can somebody just give me one thing that would be like, this is a bullshit thing?
Like what do you mean?
Yeah, like, I mean, could I, if I had an infinitely long horn that kept getting tinier and tinier, right? So this is getting narrower and narrower. Could I fill it with paint?
It's a lot of pain.
It's a lot of paint, but it's not actually. It's only pi gallons. What's the problem physically, like just physics-wise? Why couldn't this happen?
Because there's only a finite amount of matter.
Finite what?
Amount of matter.
Yes. Yes. But why would that keep this from filling up? It's you're getting to the right. How big is an atom? I mean, I don't know the answer, but there is an answer, right? So like a paint atom has a certain, whatever the atoms that make up paint have a certain diameter.
Yeah.
Eventually this will become 0. So at some point the paint would have to choke up inside here. It literally couldn't fill the whole thing simply because of the nature of reality, right? So like the paint couldn't fill this because eventually this is too small for an atom to fit down in. That's part of the nonsense of this all. But I don't know. I ask you to just think about this over the weekend with a beer or whatever you have with your friends, whatever, you know, nice sparkling cider, whatever, water, freaking water and some cookies. Tell your friends about this. Think about this because it's really, really weird, Kendra.
This might be a weird question,
Yes,
but
this is already a weird
if
conversation.
you took the horn filled with paint and you got another horn and put it inside of that, wouldn't they fit into each other so then the outside would be covered in paint?
Yeah, that sounds, you mean the same horn essentially? And
Same
just
horn,
kinda,
you just like
yeah.
stack it like cones.
Yeah, I would agree with that.
But then how could the volume?
Here we go. Here we go. Yes.
Because even then, you're talking about how like the paint atoms get teeny, teeny, tiny, and they can't go beyond.
Yeah.
But the cone itself keeps getting continually smaller. So if you put it inside of another cone, it can keep going through that point.
Yes. Agreed. But we did the math, Kendra. So a lot of this comes down to, and I'm going to bring this back up, Cassie. Sorry, we're going to do this. Sorry, but the fact that when this is actually the result of infinite sums, right? Like all this, anytime you see this integral sign, you have done an infinite sum. I hope that you got that out of this class, if nothing else. There's a lot of infinite sums going on. Anytime you have an infinite sum, shit just gets weird. Right? We talked about this thing, and this could either equal 2 minus 2 minus 2 could equal 0, or it could equal 1 plus 1 minus 1 plus 1 minus 1. And it could equal 1, so this could equal 0 or 1. Weird stuff happens when infinity enters the game. When infinity enters the chat. Infinity has entered the chat, shit gets weird. Remember this one? So close your eyes. I'm just kidding. I know you're okay. Remember that? Infinity has entered the chat. Time to close the chat or get weird. Get really weird. So, we'll actually talk more about that a little later on in the semester. I just wanted to show you the first, like probably one of the first great paradoxes of math that you have seen. Lou?
What about the Planck length?
The what?
The Planck length?
Planck length? Oh yeah. Go elaborate.
Because like, technically we can't have physical objects like that.
Yeah, there's like a minimum resolution to the universe,
Uh-huh.
right? The Planck length, yeah. So yeah, I mean, mathematical objects, as much as we'd like them to model reality, easily depart from reality. So I guess that's kind of the lesson here. But just think about that day. Tell someone about this paint can. Just do me, no? I should make it an assignment. You have to videotape. You have to make a video of you confronting someone about this paint can. And watching them just look at you like you're out of your fucking mind or whatever it is. Anyway. Okay, I'm done. Thanks. Thank you. Thank you. Yes. That's the end of Dr. T's story time. Let's get some finite problems done. Anybody have anything they want to talk about off that assignment, just right off the bat?
Yeah.
Cool, which one?
So, problem 8.
Okay. You got it there?
So, it just gives me one function, so it's not bound. So, it's a problem, it's not bound for anything.
Okay, can I see the, yeah. Thank you, Lou. Cool, okay, Lou's asking me about number 8. I'm gonna take a look at it here together. So this is a shells problem we've got. Well, I'm gonna have a slightly tweaked version of this. So we're gonna revolve this around the x-axis. Find the value of that. So it's saying the region enclosed, and I think what your trouble is what is the region, is that right? Okay, let's take a look here. Oh, okay. Gabriel would be happy. Let's just say that. So let's do y equals x to the 4th. Lou's was actually y equals x squared. Y equals x to the even. They all look like this. You can always draw them like that. 4th, and we got x equals 5, so like so. And then y equals 0 is this. So the region we're looking for is this one here, Lou.
Okay.
And you see why Gabriel would be happy, right? Gabriel's chamber pot. Whatever that is. Any other questions? No more questions ever now. I'll come around and check with everybody. Got anything you want to talk about?
Dr. T, should I stop this?
Oh, I'm sorry, what was
Should I
that?
stop this? Recording?
Let's leave it running just in case we talk about some stuff. Thank you, Josh, I appreciate it. One sec. Oh, sorry. Beautiful. Oh, you're done? Oh, okay, yeah, yeah. Yeah. God, the pictures are beautiful. My God, these are amazing.
Yeah, but I still don't get
Okay.
why, like,
How the formula is derived, is that what you're
I
saying?
think so.
Yeah.
Like, I understand this part. Kind of this part. It was more just like,
Oh, okay, this part right here in particular is a little, okay. So let's take this. It's the only thing I got. I don't have like a magazine, which would be perfect, because it has a little thickness, but this does have thickness, right? So we've got this, and we want to find its surface area, or its volume, actually, its volume. So would you believe that it's good, that the surface area would be this, the volume is the surface area times its thickness, or is that part? Well,
you'll,
yeah, yeah, because, so if I were to take the cylinder and unravel it, then the volume's easy. It's length or width times length times thickness.
Also just nice notes, it just easier to have.
Yeah, exactly.
Since it's
Yes. Yeah, exactly. And so, when I know the radius of this thing, then I know the circumference, 2 pi times that radius. And the circumference turns out to be the length. The height of the function, or the top minus bottom part, is this length. And then the dx is, the delta x is that thickness.
Oh yeah, that makes more sense.
Awesome, well, that was easy. Cool.
But then, like,
Yeah.
since it's like, this shape is like easier to,
Yes.
but for something like this, it's like kind of hard to visualize.
Like visualize what it would look like actually spun. Yeah, so this is gonna look like, kind of like a gasket.
Yeah.
Yeah, with a round bottom on it. So, imagine like,
And then it will be hollow.
correct. Yeah, so it's like a donut. It's like the bottom half of a donut where you've kind of pinched the side together. So take a donut and cinch the outer edges together so that it looked like, kind of like a UFO, kind of, right? So like I've got a donut, and like a cross section of the donut maybe looks like that. I think. Yeah, and not quite as much concavity, but like kind of like that, like a little teardrop shape. And this is just a cross section of the whole donut. So if I were to look at the whole thing together, it would have this sharp outer edge, and then like kind of cross sections like that. And then there's this hole in the center. It's hard to. And actually, and then top half of that, just top half of that. So just take this and spin it. You're gonna have a thing with a flat top, hole in the center, and then the bottom is gonna have this curvature to it on the, but think donut, think weird donut. Does that make sense?
Yeah.
Kind of, okay.
I mean, that's all, just the.
Yeah, yeah. Is that it? That was easy. That was fun. Thanks. And now we got a thing to talk about. Oh, nice. Oh, that's great. You can feel free to leave if you want, but you're welcome to stay too. Josh, you got a call. I'll be back to check with you, Dan. Josh has got a question.
I'm doing.
Oh,
It's
sorry.
right over here, sir.
All right.
Like the 2 pi one.
Mm-hmm.
I just did 8.
Okay. Okay. Yep, you did a great job. And then you're rotating around 1. So you've got this set up beautifully. This looks great, Josh. You getting the wrong answer? Let me read it and make sure that we're actually. So we've got y equals x squared Oh, so this is being rotated around the x-axis.
That
If this was
okay.
around x equals 1, this would be
Oh, I
beautiful.
saw X equals 1.
Yeah,
I thought
yeah.
it
No,
would
that's the
rotate.
cutoff.
Oh,
That's the
okay.
cutoff, but, so it's a lot easier than to make
Yeah.
it. Yeah. No, that's it. That's easy.
Yeah, okay.
Sometimes it helps to have someone read with you, you know? David, did you have anything you wanted to talk about?
Not yet.
Okay. Hello, my friend. Got anything you want to talk about? Okay, that's cool. That's cool too. Okay. You know where I am. Bye. Have a good weekend. How about you, Carla? You good? Or you want to talk about anything? Do you want me to give you a few to kind of like think it through without me watching? Okay. I know that doesn't help. Lou, you got anything you want to talk about besides that one we did? That's wrong, right? Let's see. Well, so let's see. So we're doing so volume around. What? Help me out. So we're going around the x-axis. So you're using the formula. Yeah, yeah. So is it surprising? Because here's the right formula.
Yeah.
Yeah, yeah. Well, you haven't entered it yet.
No.
Okay, I'm coming back to it. Goodbye. I'll see you later. How about you, friend? You good?
There's two that I'm getting stuck on. One of them was the one I did the other day, and I just got mad at it and I stopped looking at it.
Oh, okay.
But there's this one, which I grabbed over here. And when I set it up, I have my little 2 pi, and it's bounded by y equals 5.
Okay.
So then it's 1
Yeah.
to 4, right?
Yeah.
Mhm. And then it's rotated around x equals -1.
Okay. Cool.
So I add 1 to it, right? And like
Yes.
the x value
Yeah.
here.
Uh-huh.
Okay.
Yeah, so that's your raise. Yeah,
And
perfect.
then I put in the x plus 4 over x, which is the equation.
That's not your top though, so now you want to do top minus bottom. Your top is, let's see, there's a different top to this thing, right?
No,
Let's look at the
it's
problem.
just 5.
Oh yeah, so there is a top though. Let's go back to your picture. Because y equals 5 is the top.
Well, I put that in during another equation back here, and I had the 5 minus this. Oh, I didn't.
Squared.
I'm a dingus.
Or not squared, yeah, squared, yes. Wait, no, is that,
I just didn't distribute
Oh.
the negative
oh, that'll
the
do it.
way that I needed to.
You're not a dingus.
I'm a little bit of a dingus, but it's okay.
We're all dingus.
It's-
Everyone's a dingus.
It just happens sometimes.
It happens, right? Okay, I'll come check
That-
on you after. There you go, you probably feel a lot
That
better.
makes a difference.
Yeah, that's beautiful.
Because I could just go through and do it, but that would probably confuse me and then I get second. But yeah, because I have the math here.
Yeah,
I just need to
Lovely.
flip the little signs.
awesome.
Deal.
Hello. Want to talk about anything? Let's do it. Okay, awesome. Let's start. Oh, so, let's see, so we got y equals 1 over x looks like that. Y equals 0 is the x-axis, x equals 1, x equals 4, so so we're taking this region
Okay.
and we're spinning that around y equals -1. So y equals -1 is actually, oh yeah, you're right. Yes, it's down here. Yeah, perfect. So when we spin it, what can you picture kind of what it's going to look like, or?
It's gonna have like a little bit of it going up.
Yeah.
And it's gonna be like a cylinder.
Yeah, it's like it's like a cross section is going to kind of look like that, kind of like that. Does that make sense?
Mhm.
Cool. So we're going to use the formula because our element, you draw a little element in there, and those are, well, I think the way I described it was we're going around a horizontal axis, right? So we're going to use the formula. Yeah, pi, e, let's get this all out here. So, yeah, exactly.
Just the one for X would be the outside.
Yeah, perfect. No, this is great. This is going good, Cassie. Where are we going to integrate from to? Right about that. Where do we start our slices? Got it drawn on there quite well. It's just starting here at this left edge.
Okay, so it's
So-
1
Mhm.
and 1, 2.
1, what's my inside? Oh, actually, we gotta slow down here a second, sorry, the outside, because we're not going around the x-axis, we're going around this line, I forgot, down here. Yes.
1 over x
Minus -1, beautiful, so yeah, so this should be 1 over x minus -1 squared. And then what's our inner radius? Which again, so you do, your bottom is just, yeah, 0 to -1.
So it'd just be -1.
And think about it, there's just a little 1 unit tube kind of coming out of there. So this is just gonna be, you can just put 1 squared there. Yes. So then that becomes 1 over x plus 1. You'll have to FOIL it out, just to be careful. And then the ones will, these ones will cancel and you'll just have a couple of power rule things. Does that make sense? Okay, I'll come check. Yes, ma'am. Yep, yep.
So these are like graphs y. So do I have y equals 5 and y x plus 4? Do I
Oh yeah, we should talk about this as a group, because I think, I'm gonna go talk about this up on the board. So let's see, you got 5 and then x plus 4, okay. Let me talk about this. Hey, what problem is that, Fernanda?
Question 9.
Question 9, you're gonna have to do something, and this is the one you were just working on, Keisha. In question 9, you've got, what was your function?
X plus 4 over x.
4 over x, and then y equaled 5?
Yeah.
Okay, so, let's do this together here. So this thing, when you plot it out, looks kind of like that. It's got this asymptote that goes off that way, and it's got this asymptote here. And then we're doing y equals 5. So here's y equals 5. Stick with Fernanda's problem here. And so Fernanda's question is, how do I find these endpoints? That's a really good question. So let's talk about setting that up. You're gonna set, you wanna find out what x values make this equal to 5. Think about that, just, does that make sense? That I wanna find out what x values make this equal to 5, and that'll give me where I'm touching these ends here, because this is y equals 5. Or just think of setting the two equations equal 5 equals this. So to solve that, we haven't done anything like that this semester. What I would do is multiply through by x on both sides. So this will become x squared plus 4 equals 5x. So here I'm multiplying by x. Do you see that move? And then I'm going to bring everything to one side. And now they've made it really lovely to factor. Yeah, and you'll get some nice clean answers out of that.
Thank you.
You're welcome. I read the restroom really fast to be right back. Cool. Oh, nice. You got -5 there. Okay. Oh, wait, so here's this. Where did the -5 come from? Because you're going around y equals -1. It's a good question, isn't it? I like the y. Yeah, and we're going around a horizontal axis here, so it's not the 2 pi formula. You gotta slow down.
Way too confusing.
Yeah, but you gotta slow down a little bit. Look at, anytime it's a horizontal axis, it's this formula. So just look at what that axis is. You're just getting speedy.
Yeah.
You're trying to knock stuff out. Yes, sir.
How would I simplify it? Like, this part, you know.
That's about it, Josh. That's it. Honestly, you just have to go through and use the power rule on each piece. Yeah.
Because I didn't.
Is that upsetting?
I just shot a
5x.
take the derivative of it, and then.
Is 4. Yeah, I mean, wait, you took the derivative of it?
Well, because I was
Oh,
still.
sorry, do you mean the antiderivative?
The
Yeah, sorry, yeah, okay, good, good, good. I'm glad that's what you're doing. Yeah, this one you
I
did.
didn't even take the antiderivative.
You did, you just rewrote it.
I just rewrote it.
It's actually, it's a natural log, right?
Yeah, that's log of 4 times.
4 natural log of x, yes, sir.
So I might have almost gotten it right.
You were getting close, yeah. You were just trying to knock it out. It's like brain surgery. Careful.
But this is where it's kind of confusing, because then there's nowhere for this to factor in.
Yeah, that's the axis.
Yeah.
So, it's this. Because here, there we were rotating, this is a very similar situation. We were rotating around an axis that was below the surface. Yeah. So what's our outer curve? Yep. Now, careful, because we need the whole distance. We need that, so it's gonna be 1/x minus -1, or +1. Does that make sense, why that's so? Okay, awesome. Yeah, that's square. Yeah, so then we do have an inside as well. Yes, yeah, let me show you. If you didn't do that subtraction, you would be finding this whole volume like this. You'd be finding that whole solid thing, but you need to take out that center. And so when you subtract off that part, it removes that volume from the inside.
Okay.
Does that sound reasonable? Awesome. Yes, sir. Is that still not liking what you're doing?
I'm actually pretty sorry. I'm actually trying to simplify it.
Okay. All right, let's take a look together. Well, you got natural log of 1. What's natural log of 1? All right, oh, I gotta come around. Okay, let me try to. I gotta keep my shoes. Okay, we'll get this. I know you want to split. Let's take a look at this. All right. Thank you. Thank you. Okay. So let me just kind of meticulously go through and check everything. Yep, and that all looks beautiful, and yes. 5x minus x squared minus 4 plus 5 minus x minus 4x. Awesome. And then, okay, let's see here. Things could have gotten weird, but just in case, I'll check. No, that's good. It's all chill. And then, yep, I love that. And then, whoa, where? Oh, that's okay. That's it. Okay. Fair enough.
I realized.
Bye, friends.
Bye, thank you.
Okay, so then we've got 2x squared minus 1/3 x cubed plus x minus 4 log x. Solid.
Okay, so
And our-
it was this.
Yeah, it must be that. And then you went from, what were your intersection points?
That's a 1 and 4.
Yeah, and that
sounds completely, yep,
I
that's
look
it.
at Bezos and it was.
Oh, okay.
it was-
Yeah, yeah, that totally checks. So here, then you put in the 4, you got 32 minus 64 thirds, yeah, plus 4, minus 4 log 4. Minus, this, I see the problem.
That one.
Because
Oh, yeah.
it's parenthetical, yeah,
Oh.
this is all
okay.
subtracting off this whole thing down here, that's your problem.
Okay, so if I just add.
So plus 1/3, minus 1, plus, well, the 4 log 1 shouldn't matter.
Okay. The one.
There you go.
Alright, thank you.
You're welcome.
Wow.
You're good, I mean, you know
Yeah,
what to do.
Yeah, this is little things.
It's just the little things.
Very, very.
Is that one working, Lou?
Yeah, it's working.
Yay! Outstanding.
Let's wait.
Thank you for sitting by your trash can today, I appreciate it.